So yes, it's a correspondence between two sets. One set we call domain, the other set we call range. But there's also something very specific that needs to happen, because there are just correspondences, and then there's very special kinds called functions. So before we actually define a function, let's define a notion of a relation. So relation is just a set of ordered pairs. That's how we define the relation. No conditions, no restrictions, just set of ordered pairs. So for example, let R equal the set of the following ordered pairs. Let's say 0, 1, negative 1, 2, 0, 3, 2, negative 1, and how about 3, 4? So is this a relation? Yeah, because the definition of a relation is just set of ordered pairs. R equals a set of ordered pairs. So yes, it is a relation. What this tells me right now that for whatever reason, 0 relates to 1. So if you see an ordered pair written as 0, 1, that means 0 relates to 1, negative 1 relates to 2, 0 relates to 3, 2 relates to negative 1, 3 relates to 4. Okay? Now, if 3 relates to 4, that does not mean that 4 relates to 3. It's not a two-way street. In order for the thing to be reversed, let's say you see we have negative 1, 2, and then 2, negative 1. So in this case, negative 1 relates to 2, 2 relates to negative 1, because you see both ordered pairs. But just because 0 relates to 1 does not mean that 1 relates to 0. Just a little piece of verbiage. It's not that crucial. But here's an example of a relation. Let's say one number relates to another number if one number divides the other number. So relation divides. Okay? So let's say 3 relates to 6, right? Because 3 divides 6, right? And I don't know, 1 relates to really anything, but doesn't work the other way. 3 divides 6, but 6 does not divide 3. So the ordered pair matters. The order inside the ordered pair matters, if that makes sense. Is that okay? Right. So this relation can be demonstrated in the following way. We can say it's, as you mentioned, it's a correspondence between two sets. First set is the domain, the collection of all inputs, the collection of all independent variables will be the domain. So in this case, domain of this relation is simply a set that has what? 0, negative 1, 2, and 3, right? I don't have to list it in any particular order. Remember, sets are unordered. I can order that set if I wanted to. I don't feel like it. But all I did, I just put all first numbers, all the x values, right? The independent variable. Now the range, that will be the set where domain is mapped to. So this is the set of all dependent variables. So what do we have here? We'll have a lot, right? We'll have 1, 2, 3, negative 1, and 4. So that will be the range of that relation. Okay, just 4 points in a domain, 5 points in the range. Okay. We can also draw a little diagram just to represent this relation. You have two blobs. One is the domain, the other one is range. So what do we see? We see a number 0 mapped to number 1, so 0 relates to 1, -1 relates to 2, 0 also relates to 3, we see that, 2 relates to -1, and 3 relates to 4. Okay? So again, so there are absolutely no restrictions on relations, just any set of ordered pairs is a relation. So if I give you this example and ask you, is this a relation? And I do something like this. I don't know. Is that a relation? That squiggly wiggly thingy? What? Yeah, because what is a relation? Set of ordered pairs. Here's a set of ordered pairs that are plotted, right? Because remember, the graph is nothing but a set of ordered pairs. So yeah, it's a relation. Okay? Now, a function is a very special type of relation that for every x in the domain, there is a unique y in the range. Now, what that means, we don't like seeing something like this. We don't like seeing one number from the domain relating to two different numbers in the range. So this type of split that you see over here, we don't like that. So this is not a function. If we didn't have that 0, everything else is fine. Okay? So we don't want to see same x value corresponding to two different y values. Okay? Example of that would be when you're working on your schedule for a semester, can you be registered for this class and some other class that also meets from 9 to 10:50 on Mondays, Wednesdays? No, right? So you cannot be in two places at the same time. So this is kind of a functional idea. You can, all of you can be in the same classroom, right? So you can have different x values corresponding to the same y value. That's okay. Because there's absolutely no issues of me having more than one student, right? But you being in more than one class at the same time, that's an issue. So that's kind of the distinguish between the function and just a general relation. So a definition of a function is a relation so that for every x in the domain, there is a unique y in the range. So when you look at the ordered pairs, there are no two ordered pairs that have the same x value but different y value. Okay? So no two ordered pairs have same x, different y. It's okay to have different x, same y, but not same x, different y. So in other words, no repetition in the x. So for example, let f equal this 0, 0, 1, 0, 2, 0, 3, 0, 4, 1. Is this a relation? Yeah. Is this a function? Yep. Why? No repetition in the x. Okay. So every x value is different. The fact that some of the y values is the same, that doesn't matter. So no repetition x. So yes, this is a function. F is a function. Okay. Any questions on this so far? What if I give you a graph of a relation? What if I go back to that pretty looking thing I drew earlier? This thing. So that's a relation. Does this relation represent a function? No, why not? What? Yeah, because like, for example, if I pick this x, right? So there are this point, and that point, right? There are 3 points. There are 3 ordered pairs that have same x value but different y values, right? So that's not a function. A quick test, and as your book presented it to you, it's called the vertical line test. If you put a bunch of vertical lines through a graph, and if you have more than one intersection with the graph, then it's not a function. Okay? So this is called the vertical line test. If you just put a line through a graph and then hits the graph at more than one point, it's not a function. If every vertical line has at most one point intersected with the graph, then you got yourself a function. Okay? So at most 1 point, meaning, well, maybe a function does not exist over here, so we don't hit anything. Not sure what just happened. But, so we'll call this a vertical line test. If every vertical line has at most one intersection with the graph, then that graph is a graph of a function. So that's a very quick way to say whether a graph represents a function. Just a few examples. If I give you something like this, is this a function? Yeah, because every vertical line has at most one intersection, so yes. How about a little circle? No, because if you put a vertical line through a circle, it intersects it twice, so it's not a function. How about a sideways parabola? No, because you put a vertical line, intersects it twice. How about whatever this thing is? Yeah, because every intersects at one point, right? How about just the graph of a straight line? Yes, is every straight line a function? No, which one is not? Well, actually, horizontal, I'm okay with a horizontal. Vertical, right? If I do a vertical line, then, you know, when I put a line through the vertical line, it intersects it at infinitely many points, so that's not a function. Okay, so this is not a function. How's that? Good. All right, so let's introduce a function notation. I think most of this stuff is rather familiar to you, is it? This function story? I mean, you've seen that before maybe, but here's some notation. So function notation. So we use this notation that's pronounced as f of x. This is how you call this, not a product. It's called, well, it's pronounced as f of x. And what it tells me is that f is the name of the function. And x is the independent variable. Now, usually we write f of x equals some algebraic expression in terms of x. How many of you have seen that type of notation? Okay. So when you see things like here's an example. F of x equals x squared plus 2. So here's an example of a function. We're using a function notation, and whatever you throw into that function, whatever the value of x is, it will get squared first, and then 2 gets added to it. And this is the function of this function. Square stuff and add 2. That's what it's doing. So if I ask you, what is f of 2, and this is kind of the usage of that notation, that tells me that the value of x is 2 at the moment, right? So the question is, what is the value of the function? The value of the variable is 2. So how do you do that? Plug it in. Yeah, so plug 2 for x. So that's 4 plus 2, and that's 6. So f of 2 equals 6 in this case. Is that okay? All right. What if I ask you f of negative 3? How do we do that one? What? Yeah, and you have to be a little more careful because it's negative 3 quantity squared plus 2. When you square negative 3, it becomes positive 9. So it's 9 plus 2 equals 11. Is that right? Yeah. What if I ask you f of a smiley face? So what do you get? Smiley face squared plus 2. Whatever the smiley face is, the meaning of the smiley face, it's squared plus 2. Right? So the idea is whatever lens in the parenthesis replaces your independent variable. Is that okay? What if I ask you f of a plus 3? A plus 3 squared plus 2, right? Now, can you do something about a plus 3 squared? What is a plus 3 squared? Can we expand that? Yeah, very good. So the worst thing that you can do with a plus 3 squared is to tell me that it's a squared plus 9. That would be wrong. But you're absolutely right. The way you do those, you think of a plus 3 squared as a plus 3 times a plus 3, and then you FOIL that. So if you FOIL, what do you get? A squared, 3a, another 3a, and 9, right? And when you combine like terms, 3a plus 3a is 6a. So this becomes a squared plus 6a plus 9 plus 2. 9 plus 2 is 11. A squared plus 6a plus 11. Is that right? Who knows how to do that without foiling? Nick, you know how to do that. What do you mean it's been a bit? I will, maybe. Who knows what I'm talking about? How to square a plus 3 fast without foiling. Does anybody know the fancy square of a sum formula? Square sums fast, Nick? I know you used to. You made to this class. When was that? It was like a year ago, right? What took you so long? Oh, for sure. Well, that's a given, but yeah, it's teacher's fault. Anyways, um, how about, well, let's see. Let's do f of x plus h. How to do that one? What? Plug it in? Plug what in? Well, tell me what to write. Like that? Yes. So you do kind of the same thing. You have to expand x plus h squared. It will become, if you do the FOIL, x squared plus 2xh plus h squared. So that is this expression. And then plus a lonely 2. Okay? Yeah, because there's nothing much I can do with it, right? There's no like terms to combine. That's it. But you got the idea. So no matter how ridiculous thing inside a little parenthesis, that ridiculous thing replaces your independent variable, right? So if, hypothetically speaking, if I had another x over here, if it was x squared plus 2x, then I would put another smiley face over here, right? Each x would get replaced with whatever inside the parenthesis. Now, in reality, the only difference between this notation and that notation is not much, really. The f of x takes the place of y. So when you look at the graphs of functions, the horizontal axis is your independent variable, that's your x-axis. The vertical axis, that's your dependent variable, the y-axis, or the values of the function. Okay? So I can actually give you this. All right, I need to calibrate the board again because it's getting out of whack every where we have, so we have a graph. It's still not doing it right. Something like this. And let's say it has this points, -2. I'm probably going to stop using the smart board because this is ridiculous. 5. Yeah. It worked fine last year. Is that right, Nick? Yep. They upgraded the software. I told them not to. But they did. 3. What works here? So I can ask you things like this. Can you evaluate things like f of 0? So I'm asking you to find the value of the function when x equals 0. So we can do this by looking at this graph. Because what is the value, what is the y value when the x value is 0? 2, right? We're looking at this point. So f of 0 equals 2. Is that okay? At the same time, I can ask you what is f of 3? And you will say 0, because we're looking at this point right here. So when the x value is 3, the y value is 0. When I ask you what is f of 4, the answer is 5. Let's say the graph stops here at 5. And I can ask you what is f of 7, and you will say Well, so x equals 3, right? So here's the x equals 3. Well, where's the graph when x equals 3? It's right here, right? What is the y value? So that's the idea. So same thing here. When x is 0, y is 2. When x is 4, y is 5. But what about when x is 7? What? Don't know. Undefined, right? There's nothing going on when x equals 7. So that part is undefined. All right? Does that make sense? How you can go from a graph and you can read the values of the functions by looking at the graph. Um, okay. So any questions so far? So does that make sense? Did it make sense? Nick? Make sense? All right. So another thing we need to talk about, and we kind of touched on that, is finding domain and the range. Now we can find domain analytically just by messing with the expression. That's what we did last time. We agreed that the only thing that can go wrong with an expression or a function at this stage is division by 0. That's what we need to avoid. Okay. Everything else will probably be okay for now. I mean, we'll be adding trouble spots as we move forward, but we also need to realize that if I give you a graph, of some function, let's say, well, let's just do something similar to what we just had. Let's say this point right here is 2, -3, and the graph goes outward. I can ask you what is the domain of this graph, of this function, and what is the range of this function. And you can judge this just by looking at what is covered on the x-axis and what is covered on the y-axis. Now the x-axis, would the x-axis correspond to the domain of the function or the range of the function? Domain, very good, because domain is all the independent variable. That's the x-axis. So think about this. You have infinitely many ordered pairs. Is every possible x value used to produce all those ordered pairs? What is not used? Or is everything used? What? Yeah, everything, right? It doesn't have to intersect the x-axis. Like, you have all these ordered pairs. They correspond to different x values. So the question is, are all x values used to produce this graph? And the answer is yes. It goes down infinitely in each direction. So as you move forward, as you move outward in the graph, the entire x-axis eventually is covered. Think about shining a light on the graph, and then the graph casts a shadow on the axis. Is the entire x-axis going to be covered in a shadow? How's that for an analogy? Is that yes or no? Yeah. So all x values are used here. So therefore, what is the domain of this function? If everything was used on that number line? What? Or just all real numbers, right? And we have a fancy symbol for that. So domain of this function is just all real numbers, since every number is used to produce this graph. Now the range is different. For the range, I'm looking at the y-axis. So if I do that whole shine a light, cast a shadow analogy, is the entire y-axis going to be shadowed? Now, what is shadowed on the y-axis? Everything above -3, including -3, right? So the range here is everything from -3, because that's the lowest point on this function, and up. So the range here is from -3 to infinity. Does that make sense? Now, one thing, and I'm repeating myself, one thing that we need to understand, that if I just give you the expression of that function, for that function, you should still be able to find the domain. Domain is usually easy to find. You're just looking for, troubled areas. While range is almost impossible to find just by looking at the algebraic definition of a function. Now what I mean by that, for example, somehow I know that the function that produces this graph is absolute value of x minus 2 minus 3. So if I just give you this without seeing the graph, can you still answer the domain question? Can you still tell me what domain of this function is? Just by looking at that. Technically, yes. So what would that be? What do you mean, well, you can cheat. This is the same thing as the graph of this function is that graph. But let's say you don't know that that's the graph. Can you still tell me the domain? How do we do the domain? What are we looking for? What is the only thing that can go wrong? Anyone? I just said that 2 minutes ago. Division by 0. Is there any possibility of getting yourself into any form of a division with this function? No, right? There's no division, so there's no danger at the moment. So if there is no danger, then the domain is all real numbers. Okay? Because for now, this is the only thing that we have to be careful with, is division, potential division by 0. Later, as we move on, we'll be adding different types of functions that might have issues. But for now, the division is the only one that can cause trouble. But if I ask you, what is the range of this function, and all you see is this, and you don't see the graph, you will have a hard time answering that question. Finding the range is hard. Domain, you're just looking for division by 0 for now. Range is a bit messy, so you cannot answer the range question without looking at the graph of the function. Who's with me on that one? All right. Let's try another example. So I'm going to draw a graph, and let's say it's something like this. Oops. And let's say this point right here is 2, and this point right here is, well, let's say it's also 2. This intercept, this point here, and this point there. Let's make this 3. Otherwise it's weird. Sorry, let that be 3. So just by looking at, first of all, is this a function? The little dotted lines are not part of the graph. They're more of a kind of guidelines when you draw a graph. Is this a graph of a function? Yeah. Now, can you state the domain of this function just by looking at this graph? Yeah. What is the domain of that function? All of them? Are all numbers are used along the x-axis to produce this graph? I was trying very hard to show that there is a bit of an issue when x equals 2. The function kind of shoots up infinitely that direction and falls down infinitely in that direction, but doesn't quite get to that point 2. There is an invisible boundary of sorts. Okay? So is there an ordered pair on this graph that has 2 for an x value? No. So 2, therefore, is not in the domain of that function. Every other x value is used among all those ordered pairs except for when x equals 2. So the domain here would be, it's a set of all x's such that x does not equal what's going on this side. I cannot even make a straight line. Jesus. Is that okay? Just by looking at the graph? Again, thinking about casting a shadow. you're going to have one little hole along the x-axis when x equals 2. That's the only place where we won't have a shadow. Agree with that? Oh, you do? Kind of. You have a question? Okay. Now, another way to express this, there are two intervals. One, everything leading up to 2. So an alternative way to define this domain is from negative infinity to 2. But then you also need everything from 2 to positive infinity. Right? So we're kind of creating a hole in our number line. Well, how do you glue these two sets together if you need both of them? What is the glue for sets? And I'm miming the glue for sets there. What is this? See the shadow? Can you see the shadow? U. It's a union. Right. I'm going to take the union of these two things. So they need both. Right? Okay. What about the range? Can you find the range of this function? So you're looking at the y-axis. Is everything covered on the y-axis? What? No, what's not covered on the y-axis? Well, or 3, since we changed that 2 to 3, right? So everything but 3. So you can say, well, the range is everything but 3, right? Now, notice how I'm just using x in both cases to define the set, because that, remember how we do the set builder? We just have a dummy variable. It doesn't mean that you have to use x for the x-axis and the y for the y-axis. You can if you want to. You don't have to, because it just builds a set. I can change my variable to anything I like, really. I can, instead of x, put, I don't know, what's your favorite letter? You have a z? All right, so x. Well, we just did x. So z. That's a z. Weird z. That still works. It's a set builder thing. So it doesn't matter which you use for variable. Now, if we use the interval notation, so it's everything from negative infinity to 3, union from 3 to infinity. Is that okay? All right. So again, if I actually write the function that corresponds to this graph, you will still be able to answer the domain question. You might not be able to answer the range question. So let's say f of x equals 2x minus 6 over x minus 2. Let's say here's the function. Can you find the domain of that function? Yeah, because what do you have to worry about? What? Yeah, dividing by 0. So when will that denominator turn into 0? What does x have to be in order for the denominator to be 0? 2. So you have to avoid 2. So everything but 2, right? Everything else will work, because any other number you plug in for x will leave denominator as a non-zero quantity. Only 2 will turn denominator into 0. So the domain here is just all real numbers except for 2. Right? Just like before, we knew that. By the way, the way I know that this graph is that function, that's just because I know. You don't need to know that. But I'm just trying to prove a point that, domain you can still answer. But if I answer what is the range of this function, you'll have problems with that. Okay? Actually, I lied. This function is not that graph, but that's a different story. It's close enough. It's close to that graph. Okay? But still, range, we don't know. Okay? So in order to find the range, you do need to see the graph. Any comments on that? No comments? Yeah. Well, if you were just given that and no other information, then you say, well, I don't have enough tools to find that. Okay? It still has a range. You just don't know what it is. And all the time when you're going to get a range question, you'll have a graph attached. Okay? So you won't see a question like this. Here's just a algebraic expression. Find the range. It's hard. You can say that. Or not enough information to determine that. Yeah. So whatever it is. So give me that idea that you understand that at this stage, I mean, later we'll probably be able to get all kinds of sneaky to find the range of this function. But not in this class. Okay? So for now, in order to find the range, you must have a graph. You can still find the domain, right? I mean, I can write this, let's say g of x equals, I can just come up with whatever function I like, negative x cubed plus 2. Yeah, that's good enough. Can you tell me the domain of this function? Anyone? What is the domain of that function? Yes. All real numbers, because there's no division. So there's no danger zones, because you can cube any number that you like, right? There's no restrictions on cubing. So domain here is just all real numbers. There's no danger in that function. But if I ask you what is the range, you're not quite sure, okay? You do need to see the graph of this function to find the range. And actually, later you'll be able to graph function like this, but if I just tell you that the graph of this function is something like this, then can you tell me the range of this function when you see the graph? What is the range of this function? Nick. Why? Is there anything below 2? We need to know. It's right there. Look at the squiggly thingy. What does the squiggly thingy start? The graph, the little squiggly thingy. Where does it start? Well, yeah, depending where you want to start. If you start on the top, so it starts all the way at positive infinity, goes all the way where? Negative infinity. So is everything covered? Yeah. So range here is all real numbers. The entire y-axis is also covered by the graph. Well, yeah, if it's kind of like a U, so there are chunks of the y-axis that are not covered. So if I give you this graph, and not even the U, it could be something like this. Let's say this kind of a weird thing. And let's say we know that this point is 2, -5, that lowest point. Then the domain, what is the domain? All real numbers, right? Now there are no gaps, it's all covered. So the domain is all real numbers. What about the range? So the range, you're looking at the y-axis. -5 to infinity, right? There's nothing below -5, so it's including -5. Okay? Well, it does matter. Because what does the square thing mean? What is the difference between, is that what you're asking? Yeah. What is the difference between a bracket and a parenthesis? Yeah, so -5, that tells me that -5 is part of that set. Infinity, we can never include infinity. So infinity always has a parenthesis. Now, here is a confession. The reason why I'm picking on Nick, because this is the only name that I know in the class. So that is sad. And so what we did with my other 099, I started learning 4 names per day. Because I don't have any, you don't turn anything into me, so I don't give you anything back. So we can go this whole semester without me ever knowing your name, so that sucks. Actually, by the way, on Friday, I'll give you something that you're going to work on, and then you give it back to me, and then I'll turn it back to you, so I'll help you with the names. So I need 5 volunteers to volunteer their names. Yes? Sarah? All right, that's good. Okay, Sarah. Pleased to meet you, Sarah. Anyone else? Let me pause that, because this is weird. We don't want that part of it. Good. So, any questions on the graph domain business? So let's recap. If I give you a function without a graph, you should be able to find the domain of that function. What are you looking for? What are you afraid of? Division by 0. So if there is no fractions in your function, then that's all real numbers. If it just has powers or absolute values, there's no denominators, you just say that's easy. That's just all real numbers. Okay? Can you do the range if I just give you the function without the graph? No. But if I give you a graph without writing out what the function is, can you find the domain? How would you do that? CJ. What? If I give you a graph? How do we know that the domain of this, whatever this is, was all real numbers? Tig. Why is the domain all real numbers? Who wants to take on that one? Sarah? Robin? Yeah? Well, because if I consider every ordered pair along this graph, that every possible x value is used among all those ordered pairs. This is whole shining the light thing. It casts shadow along the entire x-axis. Is that okay? You see what I'm talking about? I mean, the whole x-axis is covered to produce all those points. Unlike with the range, because there's something that's not covered, right? There is no graph below -5, right? So that chunk is not part of the range. So that's why we only started our range from -5 to infinity. It starts at -5 to infinity, while the domain, the whole thing is covered. Is that okay? All right, well, let's try this one. So I'll give you a graph. So let's say we're going to start here, apparently, and then we're going to go on and stop here. So let's say this point is -3, and this point, wow, is +5. And let's say this point, what would that point be? So let's say 3, 1. Is that okay? 3, 1. Can you tell me the domain and the range of this function? Well, you need more information. How about this point? This point is -1 and 5. Oh, wow, this is not writing where I wanted to write. How about we cheat a little? Can I cheat? No, I cannot. Yeah, I can. I'll drag it here. It writes well in this corner. So -1, 5. So can you tell me the domain and can you tell me the range? So think about the whole shadow thing. What is covered on the x and what is covered on the y? So what is the domain? Right, -3 to 5. What is used along the x-axis? It starts from -3 and ends at 5, right? This point is that, 3, 1 is that. So the domain is including -3 through 5, including 5, right? What about the range? Yeah, so it's the lowest point is 1, the highest point is 5. So you're kind of looking at the possible y values. Everything in between is covered, nothing outside is covered. So it's from, yes, when you use the interval notation, order does matter. Because we're not just listing the elements, because it's continuously filled interval from 1 to 5, including 1, including 5. All right, good. Well, let's take a little break. I'll try to calibrate this thing again. All right, so I want to talk about this idea for a little bit. So you saw us earlier today somewhere here. We were squaring things. Remember that part? We did the FOIL, blah, blah, blah. Now, we do need to know how to do this fast, so I'll refresh some of your memories, and we'll eventually going to start using those formulas a lot more often. So let's just call this a square of a sum formula. Which means you have a sum, and you're trying to square that sum. So again, it does not just equal a squared plus b squared, as you might have noticed earlier. Actually, those type of things make me sad. So it's not a squared plus b squared. But as CJ pointed out earlier, we have to FOIL this thing, right? It is a plus b, and when you do the FOIL, it's a times a, that's a squared, ab, so that's ab, another ab, and b squared. When you combine like terms, ab plus ab is 2ab. So it becomes a squared plus 2ab plus b squared. Is that okay? There's just a little FOIL. You can recreate that. It's not that important. And if I had a minus inside this parenthesis, if this was square of a difference, then with the same type of computation, we'll end up with a negative 2ab, but then positive b squared, if we did the FOIL. How many of you have seen this formula before? Nick, yes, very good. Yeah? All right. So we need to start using this formula. You can still FOIL, I'm okay with that, but I would be really happy if you start using this formula to do those multiplications fast. So for example, if I ask you to do something like x plus 4 squared, the way we do this computation, we say, well, just match your expression with the formula. What is playing the role of a? X, and what is playing the role of b? 4. So the formula tells me square a first, so that means square x. So that's x squared, right? And then the formula tells me plus 2 times a times b. Since x is a and 4 is b, that's what goes there. And then finally, b squared, and again, the role of b is played by 4, so that's 4 squared. Is that okay? So for every a, I put an x, for every b, I put a 4, and then I can simplify this. That becomes x squared plus 8x plus 16. Is that okay? We should be able to do this faster without writing out this middle step, because at times this middle step is actually confuses you more than helps. We should be very happy with getting x squared and 16. Those are simple. You just square the first, you square the last. The way to get the one in the middle, the 2ab part, Because AB is just the product of both terms. So if I multiply x and 4, what do I get? If I just multiply that. Yeah, so what do I get if I multiply 4x? 2 means to double that. So I need to multiply x and 4 and then double that product. So it's 4x times 2, 8x. Okay? So we can do that a lot faster. How about 3x plus 2y quantity squared? I'm going to try to do this in one move. A is 3x, B is 2y, right? The formula tells me square the A, so I'm going to square 3x. What do I get if I square 3x? 9x squared. Plus, the formula tells me multiply 3x with 2y. If I multiply 3x and 2y, what do I get? What? Yeah, so what is 3x times 2y? 6xy. You multiply 3 and 2, right? So 3x times 2y is 6xy. I need to double that. So if you double 6, that becomes 12. You're not squaring 6, you're doubling. So that's 12xy, and then plus 2y squared. So that's 4y squared. You get the same result if you FOIL. And again, as I said, it's all right if you FOIL, but at some point, you need to get comfortable with this formula because we'll use this formula, and it really is going to help us to factor. Going backwards makes it a lot easier to factor expressions like 9x squared plus 12xy plus 4y squared. It's hard to factor without noticing that it's a part of this magic formula. Okay? So you need to know this formula, basically. It shows up a lot. It shows up a lot in college algebra. It actually gives us, this formula gives us one of the ways to solve what we call a quadratic equation. We'll probably do it this semester. But another way to see where this formula came from is, so here's that formula. And I mean, we also have to understand the whole algebra arithmetic thing first came from geometry. They were first doing geometry before anything else. And there's a lot of our algebraic language comes from geometry. Because if I ask you, can you pronounce this expression? How do you call it out? A squared, right? Why do you say squared? Well, you said a squared. You're right. I'm not saying you're wrong. But why is it squared? Why is it not a chaired, a tabled? Why is it squared? So somehow the little 2 tells you to call it squared. Yeah, so that's a perfect power too. Yeah. But why do we call, you know, if I ask you, what is this? You're going to say a to the power 11, right? You know, you don't make up another term for 11. You don't go a. Well, you kind of, yeah, maybe. Because if you think geometry, right? Yeah, if I give you a square of a side A and I ask you find the area of that square, you go a times a, right? So it's a to the power 2. So a squared corresponds to the area of a square of side A. That's why a cubed, if I write this, a cubed, 3 becomes cubed because that corresponds to the volume of a cube, a, right? That's where the language comes from. It comes from geometry. So that's why we call a squared, because it represents literally a squared. So if I take that logic, and I'm going to play this little game, so a squared can be thought of as an area of a square, that's a square, of a side A. So this is a squared. Are you okay with that? Now, little ab, that, again, from geometry, if you just multiply 2 numbers, it can represent the area of a rectangle. You agree with that? It doesn't have to be a square, because a does not have to be equal to b, but AB can be thought of as a rectangle, right? The area of this rectangle is A times B. Do you agree with that? Just from geometry? How many of those rectangles do I have in my formula? 2, right? It's 2AB. So I have one little AB. I can put it over here. A little b, sorry, little b, little a. So this is AB. And I can put another rectangle over here. So this is AB, right? Is that okay? I mean, I'm just moving shapes around. This is fun, just playing with shapes. Now, what is this little thing here? What is the length of this side? Yeah, that's a B and that's a B. So that's a B squared, right? Just from geometry point of view. Now let's look at the bigger picture. What is the length of this side right here? The length of the side of the big, whatever that is. What is this length here? It's A plus B, right? So it's A plus B. And what is the length of this side? A plus B. So the big thing is also a square, right? And what is the area of the big square? It's A plus B times A plus B, which is A plus B squared, right? The big square is A plus B squared, which is A squared, 2 ABs, and a B squared, right? Isn't that cute? You can draw a bunch of rectangles and squares to prove an algebraic formula. Say yes. Yes, that is cute. Although it's a little bit weird and an overkill, because clearly we can just FOIL to come up with that answer, but you'll see me drawing this picture again when I'm going to start solving equations. And this little corner over here is going to end up being very mysterious. We'll be searching for that little corner. So keep that in mind. It'll come up. It'll come up. Not today. It'll come up. So just for funsies, do this one for me. 1/2 x minus 4y squared. Do that one. And let me go get something. So what did you get? Well, give me something. What was I writing with? Where's my little... So what did you get? What? No. Anyone else? Yeah, so 1 over 4 x squared minus 4xy. That's right. Good. You square the first, that's 1/4 x squared, right? You square the last, that's 16y squared. In the middle, you multiply the 2. Half times 4 is 2, but then you have to double that. That's 4. Using this formula. Well, again, remember, if it's a minus, it's a minus. Anyways, you'll get more practice with that. You can still get those answers by just foiling. But just a little bit of a preview. Okay, so I have a little worksheet for us to work on.